Glad to see you are tuning in for the second part of climate change and agricultural water management. In the previous part, we focused on ag water management for wetter conditions, and now we will turn our attention to a drier region. The learning objectives for this unit are to explain how technological advances over time have led to an increase in water use efficiency, discuss benefits and challenges of withdrawing water from aquifers to irrigate crops, and identify how climate change has influenced and will continue to impact the Ogallala Aquifer and agriculture in the High Plains region. Most of the Midwest receives 30 to 50 inches of precipitation each year, the timing of which is adequate for supporting rain-fed agriculture. In fact, we have previously discussed that in this region, which has poorly drained soils, agriculture benefits from subsurface drainage. Here is an example of drained rain-fed cropland in Indiana, a couple miles north of Purdue's campus. Moving west to the High Plains, annual precipitation decreases to 15 to 30 inches per year. Here is an example of mixed rain-fed and irrigated cropland in Nebraska. You can see the irrigated areas showing up as much darker green. This map shows irrigated cropland by county based off the USDA 2012 Agriculture Census. You may have seen it before when learning about water scarcity indexes. You can see the shift in agriculture water management with increasing irrigation towards the west. You may notice that in eastern Arkansas and Mississippi, there are high amounts of irrigation which are used to flood rice fields. Today, I would like to focus on the irrigation in the High Plains region. In this region, irrigation is sourced from groundwater, and water resources have become a growing concern. In 2015, the USGS calculated 37% of the total water withdrawn from both surface and groundwater sources was used for irrigation. This graph shows the breakdown of how states use their withdrawals. I want you to focus on the green color, which represents irrigation. In general, when looking at Midwestern states, you can see there is low amounts of irrigation, with the exception of irrigation for rice in Arkansas and Mississippi. Looking at states further west in the High Plains, you can see an increase in irrigation use. There are many types of irrigation. Here we have examples of three commonly used methods. First, there's surface irrigation, where the soil surface is covered or flooded with water. This method tends to have the highest losses of water to evaporation or runoff. Farmers can increase their irrigation efficiencies by leveling fields and capturing and recycling irrigation runoff water. Second, we have sprinkler irrigation, where water is sprayed over or under a crop canopy. This is very common in the Central Plains. This is an example of a center pivot, which is responsible for the circular field pattern seen from above. Third is drip or micro irrigation, which is one of the most efficient technologies in terms of both water and energy. Drip irrigation delivers water at a very low pressure directly to the root zone, so less water is lost to evaporation or canopy interception. Sprinkler systems can be made more energy and water efficient by lowering their spraying position and decreasing the spacing between the nozzles. Here you can see how this decreases the amount of water that is lost to wind drift just by applying water below the canopy. Second, by decreasing the pressure of the applied water so it is delivered more directly onto the soils, we can further reduce evaporation loss as well as erosion. This is an example of a low-energy precision applicator, or LEPA system. Over the past couple decades, while total irrigated area is increasing, there is a decrease in irrigated areas implementing the less efficient surface irrigation, shown here in dark blue. Here is an example of changes in irrigation technology for the High Plains Aquifer in Kansas. You can see over time a decrease in the less efficient technologies and an increase in the more efficient LEPA sprinkler systems. On the right is an example of water use and yield benefits. In the top pane, we see that irrigated yield benefits for different crops are relatively stable, and the green line representing corn shows it receives the highest yield benefits from irrigation. In the middle pane, we can see that the amount of water applied to all crops has decreased over time. This results in increasing water use efficiency, which is shown in the bottom pane. This means that we are losing less water, so crops are receiving the same amount of benefits and farmers are able to apply less of this precious resource. The Ogallala or High Plains Aquifer is the source of water used in agricultural production in the High Plains. It is also the source of many municipal and rural drinking wells. Even though it covers a large area, it is important to remember that the aquifer is not uniform underground. It ranges in thickness from 200 to over 1,000 feet thick. Approximately 2/3 of its entire volume is stored under Nebraska and only 1/10 in both Kansas and Texas. Although climate varies greatly across the High Plains, the average annual precipitation received by the aquifer is 12 inches per year, and the average annual recharge is less than half an inch. Water table depth varies based on aquifer properties as well as the intensity of pumping of groundwater resources. In this semi-arid climate, crops such as corn, wheat, and cotton depend on irrigation. The Ogallala supports 30% of the irrigated agriculture in the U.S., which is worth $3.5 billion. The figure on the left shows how the distribution of crops shifts from corn in the north to wheat and cotton in the south. Roughly 40% of American cattle depend on water sourced from the Ogallala to drink and irrigate the grains they consume. It takes a substantial amount of water to produce agricultural products in this region. Evapotranspiration demand is the primary component in the water footprint for each of these products. Smaller fractions of their water footprint are attributed to transport and processing. Irrigation has intensified in this region since the 1950s. As technology has improved, it has become easier and more affordable to install wells. Increasing irrigation is beneficial to farmers as it reduces year-to-year variability and increases crop yields. The center of this figure shows the significant rate of change from 1999 to 2017 in irrigated area, where areas of increasing irrigation are shown in red and decreasing are shown in blue. On the left and right side are visualizations of this change in irrigated area, where more recent deactivations on the left and installations on the right are shown in greens and yellows. Studies have shown that irrigation may impact weather. For example, this study using weather observations found that July precipitation from East Kansas to Indiana increased 15 to 30% between post-intensive irrigation and pre-intensive irrigation periods. These changes are observed downwind of the Ogallala Aquifer and coincide with peak irrigation season. Even though it is interesting that irrigation may have the capacity to impact weather, it has a greater impact on groundwater resources. Earlier this semester, you were introduced to the concept of a cone of depression around a groundwater well. When groundwater wells are close enough to interact, their cones of depression have an additive effect. Many irrigation wells are high capacity, meaning they can pump large amounts of water and tend to be deeper than domestic wells. One issue that families face in the southern portion of the aquifer in states like Oklahoma, Kansas, and Texas is that the water table is often drawn down below the depth of domestic wells, highlighting how the private costs of installing deeper, high-capacity wells is less than the combined social impact of limiting access to drinking water in rural areas. Here we can see change in groundwater levels from pre-development to 2016. The northern portions of the aquifer are less impacted than the central and southern portions, which have areas with over a 40-meter or 150-foot drop in water table. Since the 1950s, pumping rates have increased over 1,000%, and current annual withdrawals are over 10 times greater than annual recharge. Issues with sustainable use of groundwater arise from poor estimates of true supply and demand. For example, in 1970, Kansas estimated it had a 300-year supply of groundwater, and only 10 years later, that value dropped to a 70-year supply. Regulations based on these significant overestimates of supply and underestimates of demand allocated more water than was sustainable. Here we see the projected depletion timeframe of the Ogallala Aquifer, assuming a continued linear trend in water level decline. The aquifer is considered depleted when it can no longer support high-capacity wells, which require a saturated thickness of at least 9 meters. At current rates, large portions of the southern and central regions will be depleted by 2100. In addition to reducing the water supply, withdrawing more water than can be withcharged from an aquifer can lead to decreases in water quality, increased costs for well installation and pumping water up from deeper depths, land subsidence, and conflicts between groundwater users. So what does the future hold in store? There is a lot of information in this figure, but let's focus on the strategic plans. In the High Plains, many states acknowledge that under status quo conditions, sustainable groundwater use is infeasible. Colorado, New Mexico, Kansas, and Oklahoma are all managing groundwater as a non-renewable resource, like mining minerals, where withdrawal permits are based on the extraction of all water resources, not on sustaining aquifer levels. There are dedicated interdisciplinary teams that are researching how to ease away from dependence on the aquifer, develop policies to aid in this transition, and research best management strategies for farmers. In Kansas, crop insurance was previously a barrier, having only fully or non-irrigated options. It has been amended to have a limited irrigation option for farmers with land over the aquifer boundary. Unfortunately, this incentive to reduce irrigation is not available for all High Plains states. In preparation for the depletion of the aquifer, some states are planning on retiring land from agriculture or planning to switch to crops with lower water demands. There are also movements and organizations supporting a switch to dryland farming, conservation tillage practices, pasture cropping, which is mixing crops and grassland, and converting farmland back to native grasslands. Playas are seasonal ponds and are estimated to provide 95% of the Ogallala's recharge. Over 80% of these ponds have been lost or degraded. Playa restoration and the creation of other recharge ponds is another ongoing effort to increase the movement of water back into the aquifer. However, even with these management solutions, future climate change will continue to exacerbate competition over these limited groundwater resources. In the northern region of the aquifer, winter and spring precipitation is projected to occur in more intense events, which could increase runoff and ultimately decrease infiltration and deep percolation in these critical recharge zones. In the southern portions of the aquifer, the climate is projected to become even hotter and drier than it currently is, further increasing the need for irrigation in the areas that are already most stressed. It is also important to note that it may be difficult to restore land to ecosystems that are no longer supported by current or near future climate conditions. In summary, we discussed how technology advances increase irrigation water use efficiency, how irrigation has made agriculture in this region more resilient, how unsustainable use of groundwater resources can lead to conflicts, and how climate change can exacerbate stressed groundwater resources and require significant changes in agriculture and water management